My name is Hyrum Wright, and you are in Large-Scale Changes at Google. If this is not where you want to be, stay anyway. You hopefully learned something. It is Friday, the last day of CppCon. I am exhausted. I don't know how about you, if anyone else is, but I'm exhausted. You know, I feel like this conference is essentially a conference about power tools. It's not even a conference about power tools. It's a conference about how to build your own power tools, right? And no one tells you how to, like, the manual to maintain them after you've built them, right? So you go home and you build some kind of chainsaw contraption with like 17 different blades and maybe a leaf blower attached because the content's expert and the compiler will give it to you for free, right? And so you go home and you build this thing, and now you don't know how to actually like maintain it and keep it going long term. So hopefully this talk, we'll talk a little bit about how at Google we've spent a lot of time investing in large-scale migration, tooling and process and some of those types of things that hopefully you can take back to your organizations. So the standard warning you get at the beginning of a very long email, right? Whoa. That is not what the warning you usually get. There we go. You can ignore this presentation if you know all your dependencies are perfectly secure, right? All the code that you depend on will always be secure forever, and that includes hardware, right? So this past year, we have discovered that your hardware is also vulnerable in strange and interesting ways, and if you do not have the ability to change your software, it becomes very difficult to mitigate against some of those problems, right? So if you know that this is true, you can go home or go somewhere else. If you will never need any features of a newer system, right? Newer language, newer compilers, newer standards. If it will never need to interoperate with anything else, right? You don't need to worry about these kinds of problems. And your code is completely bug-free. So if you meet all these criteria, then this is probably not the talk for you. Everyone's still here. So I'm assuming that you have the same problems that we do, right? We live in an environment in which our software needs to change. And your software will change, whether it be a hardware vulnerability that gets discovered and all of a sudden you need to upgrade your compiler on a moment's notice, or whether there's a vulnerability in a core library that you use, right? Your software will change. We practice the technique of doing database backups and restores and these kinds of things for disaster mitigation. How often do we practice the technique of changing our software at a moment's notice because we have a problem in some dependency? Right? That's not a thing that we usually think about, and yet being able to do those kinds of maintenance processes will become more and more important as more and more things like this get discovered, right? So I saw this a couple years ago, and it's stuck with me ever since, right? The older I get, the less I care about making the correct decisions a priori, right? And the more I care about being able to change them. I am not a perfect engineer. Don't tell my managers that. But I care less about naming something the right way or making the correct decision as long as I can go back and fix it later. And so being able to do migrations on a large scale, and large means different things, is an important thing. So what does that mean? So in Google, we have, some of you may know these things already, we have a shared monolithic code base. Right, we have a very large code base. We have, 60K changes per day, 2 billion lines of code. Hundreds of millions of lines of that is C++. This code base is a shared software repository of many different languages. There's a hierarchical ownership model within this code base. So even though we're all in the same repository, not everyone can make changes to every directory in that repository. Certain teams and projects are given ownership of different parts of the repository, and it's transitive, so owners of parent directories can make changes and approve changes to child directories, this kind of thing. And everything builds from head. So as soon as a change goes into the repository, it's live for everybody, all the other projects. So if you're making a compiler change and you upgrade your compiler, all of a sudden everybody gets that upgrade. Okay? That can be a scary proposition if you're working on the low levels of the infrastructure stack, like I often do. There's also a saying that we have around change. So your systems are going to change. There's a saying that we have that we don't want any haunted graveyards, right? No haunted graveyards in your code. We have these in our we have this saying around our production systems, We don't want systems that everyone is afraid to touch. So somewhere, I'm sure, in your organizations or maybe somebody else's, there is a PDP-11 emulator running on a System 360 emulator, running on a Windows 95 emulator in the cloud, right? Because somebody was afraid to touch that system. And so they just kind of boxed it up and put it off on an emulator somewhere. I see people laughing because they know this is true, right? They put it off in an emulator somewhere, and then that system became untouchable, and so on and so forth. We don't want any haunted graveyards in our production systems, and we don't want them in our software. We don't want to have areas of the source code repository where people are afraid to make changes. We want to be able to make changes as we need to. By the way, I forgot to mention the ground rules up front. This can be an interactive experience, so please, questions, comments, rebuttals as I go along. It's more fun for me, more fun for you. I'll repeat them for the benefit of the viewing audience at home. But yeah, so if there's something you strongly disagree with, please let me know. Yes?
It's not a disagreement, but rather a thought of code is not binary, right? So it needs to be built and then tested.
Right.
I don't understand how it can be done in a monolithic.
So code is not a binary. It needs to be built and tested. The tools that build and test your code are also part of the repository. Right? Everything that builds everything you need to build your software, or at least at Google, everything you need to build the software is in the repository. It's versioned along with the code. So when we talk about building code at a certain date or a certain revision number, that is unambiguous. What set of code and what set of dependencies and what set of compilers, everything to that effect that we're using.
So before you check in your code, you want to test it?
Yes. We'll talk about testing in a little bit. Right, so we don't want to have hidden places in the repository. Okay, Matt.
How do you contrast a graveyard with Chesterton's fence? Don't destroy a fence unless you know why it's there.
Yes, so how do you contrast the graveyard with Chesterton's fence? Good documentation. If your software has appropriate documentation around it, it's easy to know why the fence is there. If it doesn't, then all of a sudden we have a graveyard that people are scared to touch. Okay, so large-scale changes. Why might we want to make large-scale changes? There are a number of reasons that we want to make them. You may be able to think of some on your own. New libraries. So new version of the standard library gets released. We just dropped a new version of Abseil this week. So if you're in an organization that uses that, you may want to upgrade to some of the newer things in there. We didn't change anything in Abseil, so if you've been using the old stuff, you don't need to change your code. But if you want to use the new stuff, right, that's a reason. New compilers. So this is a frequent thing, I'm told, by the compiler folks. I'm not one of them, but new compiler ships, and all of a sudden, your code starts failing. Right? Anyone had this happen before? And why does your code start failing with a new compiler? It's because there's bugs in the compiler, right? No. Also yes. Occasionally, right? Oftentimes it's all together now? Undefined behavior, right? Like you're depending on a certain part of the system that is undefined. You've happily gone along with that, and the compiler has done one thing, and it's within the prerogative of the compiler to change that behavior, and all of a sudden, when you upgrade, you've got a problem. Right? Your software no longer does what you expect it to do. New language standards. So a new standard comes out, you want to use the new things, because they're awesome and fun and nice. At Google, one of my personal war stories is, and I may have talked about it in CppCon context before, when C++11 was released, it gave unique pointer. Unique pointer is a wonderful thing, and we should all be using it. We had a thing at Google called scoped pointer, which was almost like a unique pointer. It didn't have move semantics because move semantics weren't a thing pre-11. But it was kind of like a unique pointer, and we recommended that people use it. And all of a sudden we said, we want to upgrade. We don't want to be running this custom pointer type forever, and we want to have the move semantics. So we need to change all 500,000 references to scope pointer to unique pointer within our code base. How do you do that? Right? The answer is very, very carefully. Yes, I was getting there. Common bug-prone patterns. So maybe there's a new compiler warning you want to turn on, or maybe you've determined that there is a problem in some idiom that people are using that's wrong, right? You can go fix all those things if you have the ability to do large-scale changes. And to address bit rot. This isn't address bit rot. This is to address bit rot. Your system is not in isolation, right? And it interacts with all kinds of systems around it. And even if your system is perfectly wonderful today, that doesn't mean that it will continue functioning next year or 2 years or 10 years from now, right? If you have a smartphone today from 2008, I'm surprised the battery still works. But other than that, it probably doesn't do anything besides make phone calls, maybe browse the web. And that's not because the phone has become somehow incapacitated. It's because the environment, the rest of the environment has changed, right? And so the environment that your software lives in will also change. You need to be able to do large-scale changes. And you might say, why do I have to do large-scale changes? What differentiates a large-scale change from a small-scale change? I'll just say your ability to make them, right? The size of code base that you're dealing with. If you're in a small organization, a large-scale change may be 100 different call sites. If you're in a large organization like Google, it may be tens of thousands of call sites, right? Large is kind of a variant depending on what size of organization and what you're willing to invest. So, atomic refactoring. We've talked a little bit about this, right? So atomic refactoring, why don't we just make a big change and submit it all at once, right? We have the luxury of having a monolithic repository, which means we could do this in theory. If you have a federated system of repositories, you can't even do that, right? Because what does it mean to make an atomic commit across multiple repositories? But atomic refactorings have several drawbacks. They're hard to test. If I have a change that touches 5,000 files and I run it through my tests, and one of them fails, which file caused that failure, right? Hard to test. They're hard to submit. At the rate that we're making changes to our repository every day, I'm going to get merge conflicts in that large change. And by the time that I sync and resolve those merge conflicts and retest, I'm going to have merge conflicts again, right? I can't even go through this sync resolve test cycle before I get another merge conflict, right? So it's hard to submit. And because it's hard to submit, it's also hard to roll back. You don't want your changes to be a one-way street. If you submit a change as part of a large-scale change that needs to be rolled back, you want to be able to do that. And so if you can't submit, you also can't roll back very easily. They're hard to review. Anyone tried to review a 50,000-line diff before? Oh, you're doing it wrong. Right, this is really hard. And that's not something that you want to do on a regular basis, right? Smaller diffs, easier to review, easier to understand. So we use non-atomic refactoring. What does that mean? Add the new thing, whatever it is. It can be a library, it can be a compiler, it can be something else, new language. Usually you add the new thing without making it the default. So users are still using the old thing, but the new thing is available for them to use. Fix all the bugs which migrating to the new thing would cause, right? So if it's a library, you start migrating people to call the new library, because if you pull out the old library, they're going to have build breaks, right? That would be a bug. You want to fix that. If it's a compiler and you find all kinds of undefined behavior, you may want to address that, right, before you make the new compiler the default. Migrating all the users. And then finally, you can remove the old thing. Often, this is aspirational, right? The old thing may continue to shamble along for a while, but hopefully, if you're willing to invest the effort, sometimes it doesn't make engineering sense to invest that effort, we can remove the old thing. So, yep, I'll talk about it in a minute. So, we've been doing this for a while at Google. 4 years ago, I gave a talk at CppCon about ClangMR, a libclang tooling thing that we use to make large-scale changes. And we've talked about some of this in different contexts. We've had several large projects which have touched hundreds of thousands of files across our code base. So what kind of things through that experience have we learned? Some of these may appear kind of obvious, and perhaps they are, but hopefully there's some takeaways here as well. So lesson 1 is testing. So tests, so how many people have a cultural norm of doing regular testing? Okay, this is more than we've seen in the past, so this is good. If you don't yet have that norm, like, stop right now and go do that, because you need to have tests just to demonstrate your software is correct. But that's not the most important function from a software longevity perspective of tests. Right? We write tests once often when we write our software to make sure that the software does what it claims to do. But tests are actually your defense against people like me. Right? I'm going to come in and I'm going to change your software. If you want your software to continue functioning as it did before, right, you will have robust tests. It's essentially this protection against change over time. Right? Your tests are the way that anyone making large infrastructure changes can verify that they aren't breaking you. Okay. So a couple of hints on this. So for a full hour-long rant discussion about testing, Titus and I gave All Your Tests Are Terrible 3 years ago. It still is the most fun talk I've ever given, and go see that. But some basic takeaways here from a large-scale change perspective. Only test your system. So that may seem obvious, but a number of times we find tests that are testing other parts of the code base, right? They're verifying that there's certain performance characteristics, or my favorite are things that make sure that like various structs have, or various classes have the right size when that class isn't even part of the system under test, right? So if someone were to go change that class, well, guess what? Now the test fails, and everyone is sad, right? So only test your system, but do test it thoroughly. So don't, as part of that, don't over-constrain your dependencies. Don't put requirements on your dependencies through your tests that they wouldn't otherwise have themselves. Do test your thing thoroughly. Do make sure that you have reasonable test coverage. And I say coverage not in terms of lines of code. I say coverage in terms of functionality. Make sure you're testing your system thoroughly. And at Google, we actually have established such a testing norm that large-scale change authors aren't responsible for breakages that are the result of stuff not covered by, that result in stuff not covered by tests. So I occasionally, not often, but occasionally will break somebody's system by making these large-scale changes. And when I do, the first question I ask is, where is the test for that? It's often the last time I hear from that person, right? Because if there isn't a test, how am I going to verify that the changes we're making are valid, that they don't break that? And how am I going to fix any potential fix that I need to make, right? I can't verify that without a good test. This actually has such a cultural, we've ingrained this such culturally at Google that we have a name for it. It's called the Beyonce principle, right? And that's essentially our tagline for if you like your code, you need to make sure it's tested, or else it will be broken by something at some point. The rate at which we're doing large-scale changes is sufficient enough that you will get broken at some point. So make sure that your code is tested. And I already went through all that. So the second lesson is to know your code base. You need to understand what's in your software. And this, again, may seem pretty trivial, but the larger your code base gets, the more difficult this becomes. Understand your dependencies, right? So it can be very tempting to build a system that just kind of depends on whatever. And what happens when something changes? Like, who depends on a given version of a given library? We have the benefit of being in our monorepository that there is one version of every single library, every single third-party dependency, every single, or aspirationally there is one version of every library. Every single third-party dependency, all the other pieces that we need, right? There's only one of them. But we still need to understand what version do we have. It's also important to understand what depends on you. If you're the author of a library and you're trying to make these large-scale changes, who depends on you? Can you answer that question? Can you do a reverse dependency lookup on yourself and find out what are my dependencies? Right? Understand the dependencies in your code base. Certain tools make that easier to do, but it's a little bit more than just grep. beyond just understanding the core dependencies in your code base, it's important to understand the semantic relationships in your code base. So if I have a function called run, and it is implemented in a number of different places, right? This is not an uncommon name of a function. I can't just grep through my code base looking for all the things that call run, because there could be many different runs that are all semantically different. So not only understanding the dependency relationships in your code base, but understanding the semantic relationships. There's tools that will do this. Kite is one of them, the one we use at Google, that can give you insight into where are variables referenced, how many callers of a function do I have, if I have 0 callers of this function, can I kill it off? That sort of thing. So understanding what are the relationships between pieces of your code base. Once you do that, discover and remove dead code. This is actually a worthwhile effort, believe it or not. Because dead code is often the thing keeping the old system alive the longest. There's often some system out there that nobody actually knows what it does. It's still running, and it doesn't actually do anything meaningful, right? Understand those systems, understand that they can be turned off and their code can be deleted. So this can actually meet with some organizational resistance because people like their code, right? A couple years ago, I went through Google's codebase and did some analysis and killed off a bunch of old stuff. And this met with a surprisingly large amount of resistance. At which point I got to have a conversation about like version control and how dead code isn't really dead. It's just kind of, moved on to another sphere. And if you like that code that much, just print it out, staple it to your wall, right? We are removing this code. We don't want to have to maintain it forever. I had a colleague once that suggested a term called the Hyrum coefficient, like looking at the number of times that I had changed a file in the last year, and that would be a measure of how dead the code was, because if I was the only one touching it, then obviously this wasn't a system that anyone else cared about. But it's worth it to invest in removing dead code. Yes?
We're having the exact same problem with that. What tool did you recommend?
So Kite is a tool that will give you dependency analysis between, or it'll give you semantic analysis between different parts of a system. It actually works in a number of different languages, not just C++. But yeah, yes? K-Y-T-E, or K-Y-T-H-E. Yeah, Kite.
And how did you get over the cultural issues with removing that code? Did they just rip the Band-Aid off?
So how did we get over the cultural issues of removing dead code? Sometimes it was actually like providing a place in the repository where people could move their code. Right? It didn't actually build, we didn't even include it in the builds or anything. You couldn't build stuff in this part of the repository, but they just felt more comfortable moving it there instead of deleting it. Yeah, it's a project haunted graveyard, yeah. So sometimes it's just a discussion with them or their manager or whoever about how this actually isn't your code, it's Google's code, so sorry. And so there's most people will come around to it, right? And some of it actually was dependent upon us improving our tooling. So we have a code search tool that we use internally to look at you can search, essentially Google search for our code base, right? Historically, that didn't work on history. And so people were reluctant to delete their code because they wanted to be able to find stuff in the past. And so we had to wait for that tool to improve to where it would search history, right? So that's a valid concern, right? I want to find something I did a year ago. It's not present at head. How do I find that? Well, if the tooling improves, then you can more comfortably delete code. All right, lesson 3, incrementality. So what do I mean by incrementality? Get small wins often. So if you're doing a large-scale change, what you don't want to do is write an entirely new system and then start moving people to the new system that's completely uninteroperable with the old system, right? Incompatible with the old system. Google uses protocol buffers, right? This is not a secret. We invented protocol buffers. And there was a API that protocol buffers used, and that was deemed insufficient. So a second API was written. This is the one that's been released publicly, I believe. That was released 10 years ago. Protobuf has been open source for that long. we still have the old API in use at Google today. There are very, very few uses of it, but because the two APIs were incompatible, it meant that you had to slowly kill off the old thing, right? And that has been a long and painful process. You want to be able to get small wins often. Another migration we've done is we did a file migration where we changed Google's core file system API. And this touched, again, hundreds of thousands of places, but instead of writing an entire new API, we decided that we'd migrate it in place. So we'd add a new function, migrate callers piecemeal to the new function, delete the old function. Add another new function, migrate callers piecemeal to the new function, delete the old function. This takes a lot longer, but it also means that you're not, well, it can look like it's going to take a lot longer, right? But it means that you're not maintaining two separate systems ad infinitum, right? I will refer you to the Python community for more discussion about that. Right, so building a new thing, as I mentioned, is often harder than changing it in place, right? So if you can, you want to migrate a system from the inside out. And this will constrain your design criteria, right? There's certain things you cannot do if you're trying to maintain backwards compatibility interop forever, or at least over the course of a migration. I think that is worth the cost of not having to maintain two systems forever. Incrementality also means that you want to make the smallest change you possibly can over and over and over again. So in our case, we would look at, when doing something like file, where we had many different functions to migrate, we would change one, we would change the next one, we would change the next one, right? These were all independent pieces in that kind of three-step process that I outlined earlier, right? There's the migrate all the users. That's what we do, right? We want to make the smallest possible change that we can, because it means that you can test that and make sure that it's verifiable. There's nothing more frustrating than having several different logical changes in a large-scale change and trying to figure out which one's causing the failure. Yes? So close, 25 files at a time. Oh, so the question was, you change 500,000 references and you're changing them one file at a time, and it's actually close to 25 files at a time.
Is there any rule for which file?
So there's or which files map together, or which file, how big that size is. So I mentioned our hierarchical directory structure, or ownership structure. We tend to clump things that are in the same directory together, right? So they're kind of broken down naturally on package or on team boundaries. Yes? How are we rolling out new compilers incrementally? So for something like a new compiler or a new library, right? Normally what you'll do is add the thing and then have a flag flip somewhere. Have a single bit you can twiddle to turn it on or turn it off. So you can run all the tests with the new thing, but it's not the default yet. Find the test failures, fix them, and then once you have a clean test run across the entire code base, then you can flip the bit, right? The incrementality in that case is I'm flipping a single bit, so I have to roll it back. I only have to roll back that one bit. This can actually be pretty hard to do initially. So I did a zlib, everyone's favorite compression library. Several years ago, I was upgrading zlib in our shared common thing. And of course, everything depends on zlib, right? It's like one of the core foundational libraries everything depends on. And this upgrade had not been done in forever, which meant that it was really hard to do. I was finding test failures in Python tests, right? Well, zlib is used for JPEG compression. libjpeg is part of the inputs to Python image library. And people had tests that were checking whether code generated the right image or not, right? So the compression algorithm gets more efficient, and all of a sudden the string of bytes doesn't match their pre-computed expectation. The image hasn't changed, but the string of bytes hasn't. JPEG is lossy anyway, right? You're allowed to actually change the string of bytes. But because we only had one bit to flip, it was really easy to test, find all those failures, and then eventually clean everything up and then flip the bit. The next time we had to do that, because we'd already built the infrastructure for the single bit flip, it was easier to do, right? And that's one of the things about large-scale changes, is that as you practice, the first time usually is really, really hard, but as you practice at it, it gets much easier to do these kinds of incremental things moving forward. This actually is time for a good segue. Yes? So the question is, how much of the getting easier is experience, and how much of it is writing the automation to help us do it? Yes. Right? So some of it is experience, and we'll talk in a minute about some of the organizational things that help with large-scale changes. But some of it is writing tooling, and that's a wonderful segue into my little aside. Right? So we have a bunch of tooling at Google to help with large-scale changes, and this tooling evolves as our experience with our operational experience with large-scale changes does. We have tools that help us make the changes. So in C++, that would include ClangMR or other tools based on Clay's lib tooling. There was a talk yesterday about that, or Wednesday about that I'd recommend you for. Sometimes, I'll admit, right? Sometimes I just use text, regular expressions, right? Search all the things, and replace them all, right? I know I feel kind of dirty doing that, but it turns out that C++ is not a regular language for many definitions. And so regular expressions don't always work, but for some subset of changes, that will work. Clang format is actually a very important part of this process. So Clang format is a good formatting tool, Clang format being one, is a necessary piece of infrastructure you need to do large-scale automated refactorings. Clang format became a thing because we were doing large-scale automated refactorings at Google. What happened was we got really good with the ClangMR or Clang tooling bits, and we could generate these large changes. We'd send them out to review, and the reviewers would come back and say that's terrible. Like, I would never write format code that way. Could you please format it? And so all of a sudden, the bottleneck became, I can generate 10,000 files worth of changes, but now I have to format them by hand. Right? This is a terrible world to be in. You don't even get to do the fun part, right? It's just like white space. And so a couple of engineers, Daniel and Manuel and somebody, went back and wrote Clang format so we could use this for these types of cleanups. The next set of tooling you need is a way to test these changes you're generating. Review them, submit them. So we have a tool at Google that we use to automate that process, right? So we'll take a large change, slice it into little pieces, independently test every piece, mail it out for review, so we can use our hierarchical ownership model to infer who the right reviewer is, mail it to them, and then once they approve it or they have comments or whatever, we can submit it. All of that is automated. So this week, while I've been conferencing, I've submitted something like 400 changes to Google's Codebase, right? Just because I have robots that do it for me, right? So that's part of the automation story. And then you want to be able to prevent regressions, right? We need to be able to prevent the backsliding for people adding the thing that you're trying to remove. So annoying, right? One of the tools we've found really useful for this is Clang tidy. So we can add Clang tidy checks that flag on the Clang attribute, the deprecated attribute, right? And that shows up in our code review infrastructure. So when someone looks for they make a change that uses the old thing, they mail it for review, and in the code review tool, it says, you're using the deprecated thing, go do this instead. So that prevents people from reintroducing the old symbol. Right? This is a very powerful tool. Yes? Yes. So ClangMR is the tool that we have built internally. There was a talk on that 4 years ago, I think, here. And it's essentially being able to run the tooling, the AST-based matchers from libtooling in parallel across all of our translation units in a MapReduce. So translation units are independent. You can parallelize this process. I can look at all of Google's Codebase in under an hour, right? So ClangMR is not because the concept is available. Like we publish papers and things like this, right? But it's built on top of our internal infrastructure. It wouldn't really make sense to open source the MR part, but the tooling parts are certainly available, right? And again, there was a talk Wednesday. Was it Wednesday? Wednesday that talked about doing this sort of thing with us, right? So I'd refer you to that.
A quick question.
Yes.
So this Clang tooling does matching based on ASTs.
Yes.
Which is awesome. But then rewriting, at least in the open source world, happens on tokens and string replacements. Do you have something that does this on ASTs too? Like doing real transformations, or is it still...
It's still text-based, right? So But the hard part is finding the AST, and the AST gives you the semantic information you need to do the text-based rewriting.
I mean, some operations, can be done easily with text-based, but sometimes you want to add an if here, put the right body stuff, and moving things around in text can be hard.
Yes. I'm sure one day we will care about that. We're still in the early days on that. Changing the AST in flight is actually a much trickier proposition than it appears at first glance. Yes?
Yeah, I can answer that, I think. So the problem when you do AST-based changes is that it's really hard to recreate code from a changed AST, right? Because people put all kinds of comments and stuff around their code, and it's very hard to basically recreate that. So we think in the end, just changing the tiniest bit you can is basically the best you can, because we've not found anybody solve the basically dumping the AST back out in a way that is reasonable.
Yeah. Thanks, Manuel. So with all this tooling, right, the saying within Google is that changes, the individual sub-changes, right, the smallest incremental units are cattle and not pets, right? Most of us, when we write code, we take weeks to craft this custom bespoke change that implements our favorite feature and has wonderful aromas and all this stuff, right? My CLs do not have a wonderful aroma. My changes are, I'm happy to let, if there's a merge conflict, just revert that thing, right? I'll come back to it later with my automatic tooling, right? Because if your tooling is sufficiently mature, then you can create stuff on the fly, right? You don't have to worry about specific changes and the conflicts or whatever may happen. You may have to look at test failures, right? Because those are bona fide. You can't just create the same change again and the test failure goes away. If it does, then you got another set of problems. But your tooling, if it's mature enough, you don't have to worry about random, small little types of things, right? You want to treat these things as cattle and not pets. I am at least a change-producing factory, and if I don't care about specific ones, right? So lesson number 4, Hyrum's law. I almost hesitate to ask, who's heard of this before? Okay, that's really humbling. I did not name this thing, so just to be clear, but it's the observation that with enough users of your system, the implementation becomes the interface, right? Somebody is going to depend on every single bit of your implementation. This is an observation that we have made over the course of doing these large-scale refactorings, right? So again, going back to the compiler example, when you have a large number of users, like a compiler does, right? The implementation, say the reaction to undefined behavior, becomes the interface. Somebody is going to depend on every single part of your system. And when any part of your system changes, it's likely to break somebody. So an example of this, if I have my notes. We're going to talk about that. So an example. In doing this file refactor several years ago, we moved everything around, right? We had a big giant header file with a lot of stuff in it. We decided to move it to different header files. At one point, we added a comment line. That's all we did. Added a comment line. Tests started breaking. Okay? It turns out that tests obviously can match against textual output. You want to make sure that the program generates certain output. Log messages are a form of output. Log messages often contain line numbers. When you add a comment to the top of a file, the line number changes for the log message, right? Someone is going to depend on every observable aspect of your system. I don't know how to fix that, sadly. I do have a couple of examples, or a couple of observations. We'll get to in a minute. Deeply mocked tests. We have a mocking framework. You can mock out individual parts of a system as part of testing it. If your test is mocking out the guts of somebody else's implementation, and that implementation changes, what do you think happens to the test? It starts failing, because they're depending upon some implementation detail of your system. This is not cool. And yet it happens all the time. So this is as much a voice of warning that as you try to change all the pieces of your system, beware that somebody is going to depend on some aspect of the system. You don't get to control that. A couple of things you can do, right? Multiple implementations, right? If you happen to have multiple implementations of core infrastructure laying around, you can use them and surprise people occasionally. So this may be temporally, this may be spatially, in the sense of like, what if you have two different compilers that happen to implement the same standard? You could run your code over both of them and see if it falls over underneath one set of assumptions and doesn't over another, right? Another example might be hash iteration ordering, right? So this is like the classic example in that people depend on the order in which a hash iterator spits back the members of the hashing type, right? The hash function, or the dictionary type. Well, if that hash function changes, then the order changes. If you have a way of changing that hash function somewhat regularly, your users will stop depending upon a certain stable ordering of that hash function. You will probably also get to go fix a lot of their tests. A lot of their tests. Because this is that particular one is one that lots of people tend to have a problem with. But just be aware that someone is depending on all aspects of your system, right? So be willing to either have the hard discussions necessary to discourage that, or acknowledge that it will happen. All these things so far have been technical things, right? Testing, Hyrum's law, these sorts of things, right? There's actually a set of organizational issues that come into play that we've had to make changes for to do large-scale changes, right? So the organization at Google is such that there's a relatively small group of people doing almost all of the large-scale changes across Google. So imagine a couple of different scenarios. One in which you roll out a new version of the library and you just email all your users, like the whole company, and say, hey everybody, the old version is going to die in 3 months. You need to migrate. Okay? This is a very common, sadly, paradigm. Or imagine a version in which new library rolls out and a team that knows what they're doing can migrate everybody to the new version of the library. This is what we do at Google. Teams that make infrastructure changes are responsible for doing the migrations for the client teams across the company. There will be, in either of those scenarios, there is a cost, right? In either of those scenarios, someone has to do the migration. In the first scenario, the person paying the cost is not the team that owns the infrastructure. So they don't have an incentive to like not do hard types of things in their library or not make it hard to upgrade. It also means every team has to look at every change and decide, should I make this change? What's the right migration path? All these sorts of things. They have to build their own tools. All of that is very expensive. By centralizing most of the large-scale changes within a single group of teams, we centralize the expertise at making these large-scale changes into those teams. Right? They're empowered by the organization to do those kinds of things. They are able to make changes across our code base, often in ways that are independent of, or that are invisible to the teams that are changing them. What this also does is it allows for scale, right? In the former case, where you have to email all the teams, get them all to upgrade, chase down the ones that don't, these kinds of things, right? That scales supralinearly with the size of your code base. It gets harder to do the more people are doing it. When you centralize expertise, that scales sublinearly. So for me, if I'm making a change to 1,000 files, right, I build the tools and I'll go do it. If I'm making a change to 10,000 files, it is not 10 times harder. If I have to go harass 10 times the number of teams, that is more than 10 times harder. It's going to take me much longer than just 10 times the effort of doing 1,000 files. That is a property you want doing these large-scale changes, right? So centralize, to the extent you can, the expertise in doing these large-scale changes. Another thing that we've done is we've enabled global owners to approve changes to the entire code base. So I mentioned we have this monolithic code base, hierarchical ownership structure. At the very root of that directory, there are a handful of people who can approve any change everywhere. This plays very nicely with making large-scale changes. And so there's an ownership group, because this is Google, we have a committee, right? There's an ownership committee that oversees large-scale changes, makes sure that people aren't trying to do things like correct all the British spelling to English spelling, or some kind of like low return set of changes. But then once a large-scale change author has been approved, they're empowered to send it to a global owner. And in many cases, the individual owners of the teams whose code is being changed don't even know that. Right? They'll get an email saying your code has been changed. Congratulations, you can move on. And these global owners, this model of global ownership really helps in being able to affect these large-scale changes. Yes.
The clients that their library is changing.
Mm-hmm.
They have a say if their code review basically.
Shouldn't the clients? So the clients whose library is changing, shouldn't they have a say? Code review. So who is the code reviewer? Right, in this case, it's the global owner. Right, so I may be making a large-scale change, and I get this thing approved by the oversight group, and they say, Matt or Manuel or somebody, who's a global owner, will you please review this? The global owner actually has a set of tools that do automatic reviews. And so they can take all of this diff that comes down, and they can run it through tools that say, like, is that diff what I expect? Yes? Okay, I'm going to approve this, right? So at this point, we've got robots reviewing robots, and Skynet's not far behind. Yes?
It is also important to go back to the cattle, not pets thing. Like, the changes that you are thinking of when we talk about, like, oh, these changes are happening to your library. Your experience, because you work with pets, is something deep and, like, magical and, like, new features and all, like, behavioral changes, all of that is happening. The things that are happening in large-scale changes are 99% of the time proven to be semantic no-op, right? We are updating syntax. We are changing from one thing that is provably correct, or one thing that we assume is correct, to something that is provably the same. And so like, having a global owner that understands why that transformation is correct is all that actually is required.
So my favorite is on this file refactor, we moved stuff around, right? And part of it was take things out of the capital F file class. There were static methods in this class, and move them to the lowercase f namespace. So the changes I was making to people's code was literally 1 bit of change, right? There is no reason I need to email the product teams and say, will you please approve this 1-bit change, right? I know that it's exactly the same. I know the functionality is going to be the same. I'd rather have, it's easier for me, it's easier for the product teams if a global owner just looks at this thing, actually doesn't even look at it, runs it through their script to make sure I'm not changing it to lowercase g instead of lowercase f, right? And then approves it. Yes? How do I deal with people's feature branches? So there are a couple of teams. So the convention at Google is not to have feature branches. It's to live ahead. There are teams that do have feature branches. So if you are a team that is doing something unusual in your development process, then part of the cost of doing that is figuring out how to interact with this large-scale change process. So there are teams that do develop on feature branches, and they've said this is how we want to work, and they internalize the cost of making sure that these changes get applied to the right branches and get then merged back up to head. So that's a cost of working in that area within Google. Yes? So the question was, does library team own the versioning for all the libraries or just ones that are impacted by large-scale changes? So different teams own different sets of libraries. The ones that the library team at Google owns are generally ones that are fairly deep in the base of the dependency hierarchy. There are other teams that own other libraries that still use this large-scale change process. If I own our database infrastructure and I introduce a new API, I may not be at the bottom of the stack, but I will still want to migrate people from the old one to the new one. I can still use the same process. Right? So it's a process that's available to everyone within the company. Yes?
Do you rerun these scripts, REST updates? So let's say I make everybody, instead of row pointers, use at least one of the smart pointers, and then you automatically change somebody's code, and the tool says it's done, but then people would do still the old thing.
Okay. So the question is, what happens after you do a migration and people start doing the bad thing again? Essentially, right? That's what cling tidy is for. Right? So if I can write a tool that does the migration, then I can write a cling tidy check that will at least flag that they're doing the wrong thing. And that's what that piece of infrastructure is for. Yeah. So we talked a little bit about this, right? Accustoming teams to accept and even expect large-scale changes. So I'm starting to be convinced that at least within Google, software engineering consists of like just kind of throwing vague ideas in your text editor and letting all the robots come along and fix your code, right? Because we have a number of different tools that are doing these automatic changes across our code base. And teams are now accustomed to receiving these types of things, right? This is certainly a culture shift. This is not one that historically we've had. And only in the last 3 or 4 years have people actually started being accustomed to like, oh, hey, like Hyrum is showing up with a change. Like, awesome, or somebody else that I know is doing this. Awesome, right? That's a cultural shift. Yes?
Is there a way to defer from solving the change? Let's say you upgrade the compiler from one version to the next. My team is not able to absorb that change right away. Maybe come back to it maybe 3 months down.
So the question is there a way to defer a specific change? So the example was a compiler update. So the compiler will usually the compiler updates some of them are transparent. You don't get to choose. Some of them, the major compiler updates, right? They'll have a window in which teams can fix things that they may need to fix. The goal is that generally the compiler teams and the infrastructure teams are the ones fixing those types of things. Often though, there will be an opportunity for teams to work on that. But then there is a hard deadline, right? Like if you feel like you need to do additional work, like you don't get a veto. And that's part of this too, is that often we'd send out a change and teams would say, I don't like this. Okay, like you don't have to like it, but the other 10,000 people who have seen this, they didn't have a problem. So can you tell me something that they didn't know? Like maybe there's not a whole lot extra here. And at the end of the day, like I own the underlying infrastructure. So if I want to delete, so I can delete the library that they depend on, the old thing, and then we can have a discussion about how their build is going to start working again, right? And that's, yeah. I have the trump card here. Like I can be nice or I can be mean, right? I like to be nice. Yes.
Do you think organizational mechanism for like I want to use something in Boost because it's not in standard yet, but when it gets into standard, we want to move everything onto that?
So the question is, do you have any organizational mechanism for I want to use something in Boost because it's not the standard yet, and then when it gets to standard, I want to move to the new thing. Yes, we call it abseil. So that's our technique within Google. Yes, back here.
Yes, so similar to the feature branch question, and even if you're not on a feature branch, maybe I have code that I'm still working on and I can't commit yet, but then this lands. You said that the team rolling out the large-scale migrations do the migration for other people, but clearly it's only done for the code that's already in the repository.
Sure.
So if I need to commit something and this landed, like is the migration tools or techniques that your team uses available to the rest of the team?
So the question is, I'm working on a change. I haven't committed it yet. You've gone and made a change to my library, and now there's a merge conflict. Can I apply this thing locally and to my pending change, right? So the tools are sometimes available, right? Because we can make them available by cling tidy to suggest changes. Oftentimes, this is less of a problem than we expect because than you might expect because we're doing small incremental changes. And if we're doing small incremental changes, merging back down to any pending changes you may have locally is a much easier process, right? So if I'm making changes that just change the capital F's to the lowercase f's, right? That's not going to be a very big merge conflict than if I'm doing this big, large change that you need to worry about. There's a couple other comments. I want to talk about a couple of things, and then we can get to them. I already mentioned investing in tooling, so I won't worry about that. The final lesson, and really the key takeaway here is that as you build systems, design them for change, right? Almost all of the stuff we've talked about is something that can be influenced by design choices, right? You can make design choices in your software engineering practice and in the technology that you build to enable large-scale changes. This is changeability. We talk about a lot of aspects of a system. Performance, how easy it is to write, right? Maintainability. Changeability, which I submit is different than maintainability, is a property of your system that you should prioritize pretty high. Because if you can change your system, right, you can change the other things. If you can change your system, then you can increase performance by changing it to a better library, or changing your APIs to a better library, your types to a better paradigm, or these kinds of things, right? So like, think about how can my system be changed when you design it. And as an example, this is a really small example, right? Consider the fact, I had to put some code on here. CppCon, I have to at least have some code in my slides. So consider this simple little structure right here, right? It's got a couple of options. Users would just index or just access them by name, right? Or I could have a class that has getters and setters and has private members, and they have, yeah, and you know, you can say, well, this is more typing, and I don't like to type, right? But in the end, this will give you, if your setters and getters are in the header files, like the compiler will inline it anyway, right? You're not paying for any performance cost. What you get, though, is you get a place where you can go and change the type. So imagine that foo changes type. I have a large-scale change where I need to migrate all of the ints to int64. Is this a reasonable thing to do? Yes, because I think we actually have people that are doing this within Google. Where all the ints to int64. How do I change that? Well, I can change my API, but that's another set of things. I want to change the actual storage down here. If I do it just in a struct, then if the int64 is incompatible with the old int, then maybe I don't have a way of doing that. If I have an injection point in my API, then maybe I do, right? It's a very simple example, but think about how am I going to change stuff? How can a system be changed? Don't over-engineer your systems. There's a fine line there. But how am I going to be able to change my system moving forward? All right, so the 0 through 6, your system will change. Make sure you test. Know Thy Codebase, Incrementality, Hyrum's Law, organizational changes, and design for change. So that being said, I have like 3 more minutes for questions, and then I'll be around to answer more. Thank you. Yes? Oh. Yes? Is my team responsible for any feature work, or is this all that we do is large-scale changes? So my team is a somewhat nebulous term for me specifically. I actually work on the tooling that makes this possible in some senses. The teams that are doing lots of these large-scale changes, their feature work is improved libraries, better types, better APIs, this sort of thing, right? So like that is a feature. And that is the feature that they are shipping, is a better set of libraries for everybody else at Google. Yes?
Is there any code that you use but you don't own? So let's say you have SSH, right? And this is an open source that is outside of Google, and then you have to somehow import it in your code, and then this automatically wouldn't want to change it.
So yeah, so the question is, are there tools, are there libraries at Google that you use that you don't own? So like the example was given about SSH or third-party libraries that then the tools would run around and fix. We actually treat the third-party libraries specially in some senses because we don't want to do that. If we do find bugs in them, certainly we can make those fixes, upstream them, and then pull it back down from upstream. Most of the time, the changes that we're making are to libraries that Google owns, and third-party dependencies won't have dependence. Like third-party libraries won't depend back into Google, right? Because they can't. They're external. Yes.
So to get an idea, what's like the most complex kind of rewrite that you did? So bit change being on one end and
the most complex kind of rewrite that
yes.
I did.
Or that the tool can do.
That the tooling can do, right? So I don't know if it's the most complex. Something I'm doing right now has to do with like time types. So if I have a constant that I know let's say it's an integer and it represents a number of seconds, and then somewhere in a file somewhere that constant is being used, it's being wrapped in a call to a factory function that produces a duration type, an abscale duration, that is a type-safe representation of a duration. That I can then infer type information, and I can go change the type of the constant, and then I can go look at all the other places that constant is referenced and update those to make sure that they account for the changed type of the constant, right? So I can do things besides just the single expression level, right? I can look at everything in a translation unit. That's the kind of stuff that at least I'm playing around with. Again, this actually isn't my full day job. I work on the tooling, not the libraries, and so this is more just stuff I do to like make sure that the tooling still works. But yeah, you can do some pretty complex stuff with the libtooling tools.
Okay, thank you.
So I'm told the session is officially over. I can be around for a little while to answer more questions, but you don't need to feel like you need to. So thanks.